where the amplitude of the oscillations get reduced, decreased, and the vertical component is mg sin theta. When a body moves in a straight line, is simply inertia, which brings the bomb to its mean position. Torque, rotating force. How do you symbolize it? Hello students, this is SD Sir from the Temple of Excellence, Vidhyaashram, Pre-University, Mysuru. A thought for the day. A book in the hands of a fool is the same as a mirror in the hands of a blind person. You lack intellectualness. You lack knowledge. No book can help you to survive. Intellectualness, knowledge are tools which will help you to survive and survive hard. In my today's session on the chapter Oscillations, I will be deriving the most important bookwork, that is to derive an expression for the oscillations of a simple pendulum with respect to its time period. Sir, idin first chapter alle madidivalva. Know the difference. This is what I wanted you all to understand. In the examination, if you are asked to derive an expression for time period of oscillations of a simple pendulum by the method of dimensions, exclusivagi, they use the word by the method of dimensions, you will follow the derivation done in the first chapter. If they simply ask you derive or deduce an expression for the time period of oscillations of a simple pendulum, what we do in today's session becomes very, very prominent. So now we start doing the bookwork. So as the question reads, we are deducing an expression for the time period, exclusively time period of oscillations of a simple pendulum. Time period of oscillations of a simple pendulum. And nenpitkoli, this is a 5-mark question that is asked always. So we start doing the bookwork. So I consider a vertical. Vertical means an iron clamp to which a fine thread is suspended, and a metal bob of mass m is attached to it. Artha madkoli. This is a vertical, an iron clamp, a rod ankolana, iron clamp. I am suspending a fine thread, and to this thread a metal bob is suspended, and the metal bob has a mass m. Now listen carefully. An external force is applied. This is the mean position of the bob. An external force is applied and the bob is released, and it reaches a point P in a time interval what I call as T. The bob was in its mean position. It was at rest, neglecting air forces. I simply pull the bob. Some external force is applied and the bob is released. Now it reaches a point P in a time interval T. So that point P becomes one of the extreme positions. So the bob is displaced from its mean position. And remember, here you have angular displacement. So the bob is displaced, making an angle theta with the vertical angular displacement has happened. Now, at this point P, I will resolve the different forces that is acting on the bob. ಏನು ಮಾಡ್ತಾ ಇದ್ದೀನಿ? At the point P, I resolve or I break the different forces acting on the bob. So which is the first force? Always the most common force, the weight of the bob. Downward force, the weight of the bob, which is mg. Now with respect to theta, the horizontal component is mg cos theta and the vertical component is mg sin theta. Motion in a plane alodidwala. Component along the horizontal is always cos theta. Component along the vertical is always sin theta. And please do know this. Here, mg sin theta is called as the restoring force. So we call mg sin theta as the restoring force. Why? It is that component which will bring the bob back to its mean position. Always remember, mg sin theta is that component of the force which will bring the bob back to its initial position. So simple in considerations. There is a simple pendulum of bob mass m. External force is applied. It is displaced to an extreme position at the point P. Theta is the angular displacement. At the point P, I have three components of the force. mg cos theta along the horizontal, the weight of the bob acting downwards, mg sin theta, which is the restoring force, which will bring the bob back to its initial position. And these are the fundamental considerations done. Now, I will now calculate the torque that is acting on the bob. Torque is a type of force, and this torque is called rotating force. There is some rotating force called torque, which is acting on the bob. And torque is represented by the symbol tau. It is called tau, which is written like this, and it is defined as the product of force into displacement. ಯಾವ ರೀತಿ torque define ಮಾಡ್ತೀವಿ? Generally, torque is defined as the product of force and displacement. And what is torque? Rotating force. How do you symbolize it? Tau. So torque is force into displacement. So tau equals, what is this force we are talking about? Always remember, it is that force which brings the bob to its mean position. Restoring force. So wherever you are trying to discuss torque, the force we are concerned is the restoring force. And here, the restoring force is mg sin theta. I told, mg sin theta is the force which brings the bob to its mean position, initial position. It is restoring the position. So mg sin theta. L, the displacement, is the length of the string, what I call as L. So force, restoring force, which brings the bob to its initial position, which is mg sin theta. L, length of that thread. So we have the torque tau is equal to mgl sin theta. So how did I define torque? It is the product of force and displacement. What is that force called? Restoring force, which restores the bob to its initial position, mg sine theta. Displacement, L, and therefore torque is mg sine L sine theta. Now, since the force is restoring in nature, the torque is also said to be restoring. So now the restoring torque is mgl sine theta. No wonders here. Same expression, specific ಆಗಿ ಹೇಳ್ತಿದ್ದೀನಿ. Since mg sine theta, restoring force, so torque should also be restoring in nature. So the restoring torque is given by tau equals mgl sine theta. If I assume the angular displacement to be very small, see, during simple harmonic motion, I cannot have displacements of large amplitude. Theta has to be very, very small. That is the nature of simple harmonic motion. Therefore, if theta is very, very small, I have discussed earlier, sin theta approximately becomes equal to theta itself. Andre, sin 1 degree. 1 is very, very small angle. So it approximately takes the value 1. 0.5, sin 0.1. So for very, very small angles, sin theta is approximately equal to theta. Remember, for small angles, cos theta approximately equal to 1. Tan theta approximately equal to theta. And sin theta is approximately theta. So the sin theta takes up the value theta. So now tau becomes mgl theta. Got that? So the restoring force now becomes mgl theta, assuming that the angular displacement is very, very small. Now, I define something called moment of inertia when I take up the next sessions on rigid body dynamics. You become familiar with these terms. A simple definition, moment of inertia. No quantum physics here. Inertia ant odidira. Resistance to change the position when a body moves in a straight line is simply inertia. When I talk moment of inertia, it is the opposition offered by a body to change its position during rotatory motion. Aste. Both inertias mean the same, resistance to any type of change. But when I speak of moment of inertia, I am considering the resistance to change during rotatory motion. So here, Moment of inertia, basically it is defined as mass into distance square. Here distance is nothing but the length of the string. So I equals ml square. Now, angular acceleration. By definition, again there you will understand. By definition, tau is I into alpha. I will derive this expression in the next chapter. Relationship between torque, moment of inertia. Here alpha is called angular acceleration. So by this expression, if I consider alpha to be A is equal to tau divided by I. That is what I have written here. Angular acceleration, A is equal to tau divided by I, or A equals, what is tau? Restoring torque. I have got an expression there, minus mgl theta. What is moment of inertia? ml square. Why this negative sign? Negative sign simply shows restoring force is opposite to displacement. Yes, beautiful agide nodi. That means acceleration is also opposite to displacement. So substitute for torque, mgl sine theta. Substitute for moment of inertia, ml square. M gets cancelled, L gets cancelled, minus g theta by I. Now, during simple harmonic motion, we told acceleration is minus omega square y, correct? For any body executing simple harmonic motion, acceleration is minus omega square y, where y is angular displacement, or here it is displacement. Comparing here, I write angular acceleration is minus omega square theta, where theta is angular displacement. Instead of y, I have put theta. I compare both these expressions. I compare this A and this expression. On comparison, omega square is G divided by L, or omega is root of G divided by L. Now we know omega is 2 pi f, as we did in the previous class. So this is nothing but omega. 2 pi f is root G divided by L. We told the same thing. F is 1 by T. Frequency and time period are inversely related. So this F is 1 by T. So finally, T becomes 2 pi root of L by G. Look at the beauty. Either you use the method of dimensions or the method of oscillations. Time period of oscillations of a simple pendulum is one and the same. This was the expression I derived when I used dimensions, and this is the one I derive when I use oscillations. So in any case, the time period of oscillations of a simple pendulum T equals 2 pi root of L divided by G. Now, we study something called as damped oscillation. What is the meaning of damping? When you say a person is damped, the exact meaning of the word damp is to suppress. ತುಳಿಯೋದು ಅಂತಾರಲ್ಲ, ಡ್ಯಾಂಪಿಂಗ್, ಎಲ್ಲೋ ಒಂದ್ ಕಡೆ ಕಮ್ಮಿ ಆಗ್ತಾ ಹೋಗೋದು, ಸಪ್ರೆಸ್ ಆಗ್ತಾ ಇರೋದು. Then what is this damped oscillations? If you look at the diagram, it is very clear there. The oscillations in which the amplitude keeps on decreasing due to the force of opposition. So it is a type of oscillations where the amplitude is damped, amplitude is suppressed, or we say amplitude goes on decreasing. Why? Due to the force of opposition. We have an external opposing force which will damp the amplitude. See, here the height of the oscillation next goes on decreasing, it goes on decreasing, takes a minimum value. This is called damping effect, where the amplitude of the oscillations get reduced, decrease due to an external force. Forced oscillations. Here, there is an external force acting on a body which will force the body to oscillate. We are applying an external aid and then make the body to oscillate. That is called forced oscillation, which means here in this case, the body will not oscillate with its natural frequency. It will oscillate with that external frequency. Whatever force is applied, that is called forced oscillation. And finally, resonance. My dear students, in physics, resonance means frequency matching condition. ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿ, ಯಾಕಂದ್ರೆ ಇದ್ರ ಮೇಲೆ ಪ್ರಿನ್ಸಿಪಲ್ ಮೇಲೆ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಗಳು ಮಾಡ್ತೀರಾ, ಸೋನೋಮೀಟರ್ ಅಂತ, where you calculate something called resonating length. So resonance means frequency matching condition. Coherence means wavelength matching condition. So here, if the natural frequency of oscillation becomes equal to applied frequency, then we say resonance is achieved. Frequency match agbeku. Which two frequencies will match? It is the natural frequency of the body matching with the external applied frequency. So students, in today's class, we have derived an expression for the time period of oscillations of a pendulum. We have seen what is damped and forced oscillations, and finally understood with what is resonance. With all these insights in thought, in my next session, I start a new chapter, a very beautiful chapter called Waves. Until then, have a nice time. Thank you.